Here we see the data between the planet distance and the time of revolution in years. The distance is given in the astronomical units. So we have for the planets Mercury, Venus, Earth, and so forth, so on to Neptune. And it is a fact uh, from the calculations and from the physical laws that the Kepler's law holds good. And it says the square of the time period is proportional to the cube of the distance of the planet from the sun. So let's plot this data in Python, and then we will change the scale to logarithmic. So for this one, I have to adjust these things here, both the screens, so that I can plot the data, since I have to type as well. Okay. So here it is. So I would like to create vectors. So the library, import numpy as np and import matplot lib.pyplot as plt. And I reserve one cell of code for importing the libraries. Then in the next part, next segment, I generate the D vector. So D vector is going to be numpy array, and I have to feed the values in astronomical units. So 0.3887, 0.723, then 1 for Earth, and 1.532, 5.203 for Jupiter, 9.541 for Saturn, and 19.19 for Uranus, and for Neptune it is 30.09. So this is the creation of the distance array. And then the next one is for time period. So T is again numpy array, right? This is 0.241, 0.615, then 1 for Earth, and it is 1.881, then 11.86, then 29.46, and then 84.01, and last one 164.8. So the two vectors have been created, right? So then the first thing is to plot. So from the library plt plot, we would like to see the d on x-axis, the distance on x-axis, and time period on y-axis. And I would prefer red circles. And also I would like to see a smooth curve. Oh, no, not that smooth one, just connecting those points. On x-axis, the label is distance, and it is in astronomical units. And on y-axis, the label is time, and this is in years, year with reference to the Earth. So we got the curve, we got the line segment, and it seems that it differs from the straight line. So now let's attempt the power law, which is like the Kepler's law. So t squared equal to k d cube. t squared equal to k d cube. So if I take the square root, so it will become k and d raised to the power 3 by 2. So if I take the log, so it is natural log, okay, log of this constant k plus 3 by 2 times k, log of d. And if I consider as log of t as y, this as a constant c, so 3 by 2 should turn out to be the slope of a straight line, which is between log of t and log of d. So let's do it. On Excel. So here I'm going to plot PLT numpy log of t and numpy dot log of t, and we expect the data to appear on a straight line. So okay. For the time being, I'm not going to write the lines for X labels, right? So it is understood because my voice is available. So it has turned out to be a straight line. But now the next task is to see the slope. We expect a 3 by 2. So uh, let's use the polynomial function. So numpy fitting function, numpy polynomial. Then we have to see another time polynomial, and then we would like to see polyfit. And in the polyfit, I would like to use log of d and then log of t, right? Since I didn't reserve any special variables to store log of d and log of t values. So I'm again calculating them in the as vector in this function. And I would like to generate the coefficients of a first degree polynomial, which is a straight line. So I expect slope as 1.5. Okay, so log is not defined. Yes, this is an error. I require the log that must be called from the numpy because I'm using the vectors. So error has been eliminated. So do you see the values? And I'm so excited that the value is consistent with my interpretation 1.499, which is practically 1.5. 1.5. Now the other interpretation from the graphical point of view. So if I change the scale, so I will get the information that the data would appear as a straight line, right? But there is no meaning of slope like the slope of a straight line, right? So I will plot the data again, PLT plot, D on x-axis, T on y-axis, and then blue circles. And PLT, I'm going to, okay, let's see that one more time. Okay. So there is going to be a slight curve. Okay. So now let's see that one with the logarithmic scale. So logarithmic scale, x scale to be log and y scale again log. So straight line. And please notice the scales. The x scale, we have one label as 10 raised to the power 0. The next unit is 10 raised to the power 1, the major unit. And on the vertical axis, you have also the multiples, the scale in the multiples of 10. You can control them with the x axis specification. And here you can see the fine lines, PLT, grid, and uh, grid should be on, and it should be major and minor both. Okay. So the lines are not equally spaced. So that is to remind that it is a plot on log scale. So now if we would like to get an average estimate of that kind of a value which appeared as a slope in the previous demonstration. So how to get that one? So that value is like, okay, I would say the constant is equal to log of, sorry, numpy log of some value, say t4 minus numpy log of t3, and it should be divided by numpy log of d4 minus numpy log of d3. So if these parentheses are consistent, then from this expression, I will get the value of 1.9778. So log of T4, log of T3, log of D4, and log of D3. So let's change that value, say 5, and consistently in distance 5, 1.83. So this is a kind of the approximate value. So let's see the procedure, but how I have used this expression. So if I start with a journal power relationship, y equals alpha x raised to the power beta, and if I take the log, so log of y equals log of alpha plus beta times log of x. So to discover the relationship, you have to refer to the equation, right? So this equation, the power relationship, it contains two constants, alpha and beta, right? So to get the values of alpha and beta, you have to generate two distinct equations by using two distinct points, and then solve this equation to generate the values of alpha and beta. So one strategy is with the 2 points. So you have y1 equals alpha x1 raised to the power beta, and y2 equals alpha x2 raised to the power beta. You can divide the two equations. So it will become y2 over y1 equals x2 over x1 whole raised to the power beta. And then to eliminate beta, you can have y2 over y1, and it is equal to beta times log of x2 over x1. So beta value will be log of y2 over y1 over log of x2 over x1, which can be written to generate an analogy like log of y2 minus log of y1 over log of x2 minus log of x1. So you will get an approximate value of beta, which is the exponent of the x variable. So which is the exponent of x variable here. Exponent of this x variable, right? So that's the relationship between the power law, the log-log scale, right? The log-log scale converts the power relationship to a straight line, right? So, however, please remind yourself again and again that if you see a straight line on a log-log scale, do not calculate anything like y2 minus y1 over x2 minus x1 to represent the slope. So, thank you very much for observing the silence. It's time to take a deep breath. It calms the mind.